He's stunning Mr. Curtis.
And inexorable, so there.
Resistance is
Exactly.
Hold on, let me get out a piece of paper for this review.
Okay, so for chapter... All this dead silence.
I don't want to miss anything that he's saying.
You won't have to, it's recorded. All right, when we started chapter 18, you know what, rather than saying specifically chapter 18, I'm going to like try to talk about concepts more. Right, so this test is going to go from electrostatics to circuits. And along that path, you go from electrostatics, right, to forces. From forces, you go to energy. From energy, you go to electric potential. And then from electric potential, you go to current. Oh, electric potential, by the way, is voltage. You go to current. From current, like resistance. Oh, resistance. And let me make that all at the same moment. Make those three together. I think from electric potential, electric potential we branch into R and I and C. For what? Yeah, forces. The forces between charges, and that allows you to have potential energy between charges, which allows you to have electric potential. And then this is what allows you to like kind of begin this whole thing with circuits, and C and I are a circuit. So that's kind of like the logical progression. We started off with electrostatics, and then in those electrostatics, we talked about how those things interact. And then from those things, we got the concept of voltage. When we looked at voltage, we looked at the components that are in that voltage relates to, and then we got to electric circuits. And of course, from electric circuits, right, we did Ohm's law, the loop rule, the junction rule, and power. Those are the big ideas. Okay, I'm going to go quickly because it's going to be online.
What did that say?
Okay, so let's start off with the idea of electrostatics. And remember, it is not necessary if you write down everything, right? Keep space between your notes. Jot down thoughts about what I'm saying. You don't have to necessarily write what I'm saying because this is all online for you to review. Yeah, also. Okay, so electrostatics. What is the fundamental concept behind electrostatics? Opposites attract and likes repel. Right? Opposites attract, likes repel. That's the fundamental concept behind that. Okay, so remember, the deal here is if we take a particle that has plus and minus, and we separate the plus and the minus, what did we have to do to break those things apart? What do you do when you move anything? Okay, use energy. Using energy means you're doing work. So some work is done to separate these charges. Okay? And if work is done to make something happen, then if that thing has energy in it, what do you call that stored energy? Yeah, potential, right? So when I take this particle that's neutral, and I rip it apart, I've done work. If I let go of those two pieces, what's going to happen? Yeah, they're going to snap back together, right? Because all of that work that I put into this is now stored as energy, right? So the work that begins or that becomes stored as energy in here is ultimately, right, in the form of what? Like, what is it that maintains this energy? What is it that allows these two to be attracted to each other? What makes this happen? The field. These are attracted because of electric forces, right? And what causes those forces, like what makes that happen? It's the electric field. Right? The electric fields coming off of these things are what makes all of this stuff happen. All right? So some general, like a general concept. Yeah, sure. Yeah, sure, I will. All right, the force between two particles is this. This is called Coulomb's law. That describes how much force there is between two particles. K is a constant.
What did it describe?
This is the force between two charges. If one charge is a plus and a plus, then what is this force? What's it doing? Repelling. If this is between a plus and a minus, what's it doing? See, it doesn't care, right? It just does that force. And that's called Coulomb's law, just like the unit of charge, Coulomb.
Is that nm squared over c squared?
Yeah, because it's just this units, right? Because if you want newtons here, then what does K have to be? It has to have newtons. It has to have meters squared on top to cancel this. It has to have Coulomb squared on the bottom to cancel that.
Wait, so if the both charges are positive, will the answer be negative?
We're dealing with scalars, so no, because like there's no negative sign. We're just you just remember what they're doing. So when we deal with vectors, I try to get you to deal with the two components separately, right? Like if you go into science in college, you take high-level math like vector math, vector calculus, then you learn to deal with vectors as single things that have direction and magnitude. But then we kind of separate them and keep them separate. So it's like we talk about the number, the size of something, and then you use logic to figure out where it points. Does that make sense? Yeah. All right. What do you call this? Yeah, work. So work is force times distance, and work is in what units? Joules. And what else is in joules? Energy, right? Heat is good. Kinetic energy, potential energy, whatever. It's all in joules. So do you see that I can get the potential energy between two charges by using this logic? So let's say I take a charge, a particle, and I rip it in half. Does it make sense to you that the amount of work that I did is equal to the potential energy that is now in those two particles? Right? Same thing like if I pick a rock up off the ground, I have to do the amount of work that equals the gravitational potential energy. Does that make sense? Okay, so if that does, then do you see that the potential energy is going to equal to force times R? Because if we go back here, if I make this distance right here, if that is R, then do you see that the distance that I had to do work was R? Right? Just to make it match. I mean, R, D, L, S, whatever, X, Y, it's all just, displacement. But what I'm doing, the reason I made this specifically R is because this is the distance between the two particles, right? Would you agree that this could also be D? Because I apply a force over this distance. But then now what I'm going to do is I'm going to say, if you don't mind, I'm going to make this R because that's the length, the distance between the two particles. Okay. Now, if I do that, I can take that equation and plug it in here and tell me what you get. Do that. On your notes. She's not here. Hey, what flavor is it?
I got bacon with beans, ham with rice, ham with beans, chorizo with beans.
Everything has beans. No? What's that?
Ham has rice.
Oh, okay. I'll take a ham and rice.
Beans are gross. They make you too.
When you say beans themselves are gross, it is simply the consequence of them.
I don't like beans either.
Are you serious?
What's that? I just don't have time for it. All right. So, what'd you get? Ann, what'd you get? Solve for P.
P?
What's this? It's up there.
Yes.
Multiply that by R. What do you get? That's it. And this is the potential energy. This is electrical potential energy. That is the potential energy between two electric charges. Okay? So we've got the force between two charges. Now we have the potential energy between two charges. Okay. Now, do you remember if I want to find out how strong, I don't know, I have a football, so I want to find out how strong it is. How do I measure how strong it is? Yeah, if I said to you, how strong are you, what would you answer? or if someone asks you that question, what are they asking you? What if you can do what? Huh? Yeah, if you can do some amount of work, like some lift, like how strong are you? They're generally going to ask, how much can you bench? How much can you squat? How much can you do whatever? So it's how much, kind of like that sort of force that you can apply. So if we kind of looked at that, we could rate everybody in here by their strength, right? Because we could rate them as, let's say, pounds per person. Like you have pounds you can lift per each individual, right? Now, if Kathleen can lift, I don't know, let's say 200 pounds, and I can lift 250 pounds, who's stronger? Okay, you see why? See, because if we compare the pounds that she can lift by her weight, then you get some ratio that gives you a strength rating. Does this make sense?
Yes.
See what I'm saying? So, okay, how do you evaluate the strength of an electric field? Well, you evaluate a person's strength by how much they can lift over how much, like, whatever, the mass that they are. There is a ratio that tells you the strength of an electric field, and that is newtons per coulomb. So newtons is how much it can lift, and coulombs is how much charge you have to put on it. The more charge you have to put on, the weaker the electric field. Now, remember, where have you seen electric field? Like you literally looked through them. You felt them.
What are you saying?
You made a device to see if you can identify those fields. Remember this, the Van de Graaff thing that was here, the big steel ball that made sparks and everybody went, right?
Yeah.
Why did that work? Why did it do all that stuff? Because of electric fields. It throws off a giant electric field. That's what made your electroscopes move. That's what makes your hair stand up. That's why the sparks happen. So that electric field is measured in newtons per coulomb. Okay? Now, what up here is in the unit of newtons? So is work in newtons?
No.
No. Is potential energy in newtons? No. Is K in newtons? Well, there is a newton in it, but it's got meter squared per coulomb squared. So it's not this. Force, right? Force is in newtons, right? Okay, so now, and what is in coulombs? What letter is in coulombs that's up here? Q. Does that make sense? Remember this? Q is in coulombs. So, if I take F over Q, I should get the equation for an electric field. So, do that. Just like I asked you to do this over here. Do it here. You have an equation for F divided by Q. Tell me what you get. I'm going to get you to agree. You have been solving? Last time you left a big stain on that. So make sure that there's no mess.
Is the salsa watery, Mr. McClure? Huh? Yeah. Smells nice
All right. Let's see. Vincent, what'd you get?
I got K, Q1, Q2, Q3 walk square.
Okay. You see force here. Q1, Q2 over R squared. R squared. That's F. What happens if I divide this by Q?
Oh, yeah, on the bottom.
This is going to cancel with that. So, what I get... That's
Does it matter which one it cancels with?
No, not really. They're all arbitrary names. Not going to take up some great. I usually get rid of it by doing a trick, but it's kind of violent.
Wait, what did she do? Why did you do that?
Because hiccup is it's kind of like a reflex arc in your diaphragm.
I had a quick crack.
So like when you do that, you send a shockwave through your diaphragm and it makes it go away.
What happens if you punch the hole through your chest?
Well, then I'd be dead. And we
What
wouldn't have
happens
this
if like you
conversation.
accidentally like broke your bone and like collapsed and then you're having
That can't be humanly possible.
Yes, it could be!
How could someone hit themselves in their own chest so hard they break their
You
chest?
tell me, Mr.
Well, I haven't done it yet, so I don't know. All right. Anyways. Okay.
That was a very scary noise though.
But it works.
If you tell me I have a hiccup and hit myself, I will stop having hiccups.
Are you sure? Can you do it again?
I've done it before, it does not work.
Just hit yourself.
It doesn't work when I do it.
Yeah, girls shouldn't do that, I know. All right. I'm going to move on past this awkward moment. Okay, so the point is, the point of all this is to show you that from Coulomb's law, we derived this potential energy equation, and we got this electric field equation. Right, so all these three things are connected. So if you take force, right, and if you multiply force by distance, you get the potential energy in an electric circuit. If you divide force by charge, you get electric field strength. Right? That's how they relate. Okay, and now there is something else. What does a volt mean? What is that? Okay, it's electric potential. But when I say a volt, what should you think of? A volt is a what over a what? Okay, remember the concept, right? Current is people, and voltage is the people's what? Interesting. Yeah, energy, right? Voltage, the analogy that I made about the school, remember? You go through your school day, what do you lose? Voltage or energy, right? So a volt is a joule per coulomb, right? It's energy per charge. So now, talk with your neighbors, work this out, figure out how do you get this based on one of these three things. Using either potential energy, force, or electric field, dividing, manipulating variables, whatever you're going to do, figure out a way to get this, to get V. Right? So do you get what I'm saying? Here, we took F, and we figured out a way to get PE by multiplying by D. Then we took F, and we figured out a way to get E by dividing by Q. So by dividing by, or multiplying by, or whatever, any of these basic variables, figure out a way to get V. So,
Get V?
yeah, get V. Basically, you're looking for the units joules per coulomb. So look at the units of those things, and you should be able to see it. I can fall asleep. You were laughing in the first second. I figured out, Eileen, I'm going to ask you.
No! What am I supposed to figure out here?
How to get those units from those things. When you what?
Can I charge it?
Sure, if you have a charger.
What was that? Oh, no. That was gross.
Okay, that was a monkey. I didn't do anything like a monkey.
That's a monkey.
Exactly. I can't bring it over.
Oh, we gotta hear the last one.
Oh, that's good.
Ready?
Force is in newtons.
Okay, so listen. Go ahead.
Force is in newtons.
Okay.
You have to divide them and it's energy or ease.
Mm-hmm.
Force is in newtons. Meter.
What unit is this?
And then the
Whoa. What unit is this? What unit is this?
N squared or wait, joules, right? Ah.
How do I get this from one of those? Remember, what do we do here? We multiply by D, or we divide it by D?
What is D?
Or not D, sorry, divide by Q. D is the distance between the particles.
So like, is that what?
That's like R.
I know, but like, what do you use for that?
Meters? Distance? So here, what do we do to one of these to get joules per coulomb? Divide what by Q? One of these units is just like the other. Come on, can you silly one?
Is that recorded?
Yes, it is. Ah, yes, see? This is joules, that's joules. So all we have to do is get coulombs on the bottom.
What about
So
that
if
W?
we take PE over Q, we will get volts because it's joules per coulomb.
But then isn't there something over the C? What is that?
Yeah, this is newtons per coulomb. So what we can do here, what can we do on this side? Take E times D, right? And that's going to give us volts also, because E is newtons per coulomb, and a joule is a newton meter. So this becomes newtons per coulomb times meters. This over here becomes joules per coulomb. But a joule is a newton meter. They match. So there are two ways to get voltage. By taking the potential energy divided by the charge, or by taking the electric field times the distance. So what voltage means is how much energy did you give it per charge. So if you think of this way, it's kind of like take a charge in an electric field and pull it. And when you pull it through the electric field, you're getting it ready to do something. So, I don't know, like maybe launch it or something. So you need to know the relationship between those four things. Force, E, PE, and V. You need to know how to get all of those. All right? And that's pretty much like chapter 18 and 19. And then chapter 20 and 21, I'll probably talk about tomorrow. But I will go ahead and put up the test prep tonight. Yeah.
Do you have to like memorize all these equations, or go on the formula sheet?
Yeah, I'll probably let you put them on the formula sheet for the day.
Oh, yeah.
Okay, so let's do a couple of simple problems to see if you can use what you've already used, or what I've said today. So let's do this. All right. Tell me, what is the attractive force between these two spheres? What's that?
So if we
Yeah, it's a negative 3. Yeah. So I'm asking you for this.
Is that 3 or is that a negative 3?
It's negative 3. Just use the equation. Huh? What? No. Use the equation. I gave you an equation. I mean, if you're trying to do it in your head, it's going to be tough. Really?
Like, no, the use of it, like,
Just drop the negative, that's all.
do you know, do you have to do it for everything?
It's just in that equation.
Which equation has absolute value?
The one that I wrote it in.
I don't see it on any of these. Oh, I really forgot to add that in.
wait, is it absolute value in like the other equations then too?
It's in PE,
Okay.
It didn't follow it. So it's an F and P.
What? This can't be hard. No?
You'd be
This
surprised.
isn't hard.
You'd be surprised.
Yeah.
Who shall I
Finished your
choose?
burrito already?
You see this guy? He's just like 2 bites and done.
See, Alan Huang, what'd you do?
Multiply 4 into 3 times
So we just do K, Q1, Q2 over R squared. So that's going to be 5, no, we're going to get 5. It's going to be 9 times 10 to the 9th times 4 coulombs times 3, I'm just going to make it 3 coulombs over 1 meter squared. And then that is going to give us 108. So it's 108 times 10 to the 9th newtons. Which is a ridiculously large force. Questions? Does that make sense? All you do is plug it in. This is the force between these two things right here. Yeah. K is a constant that I gave you. I said K was 9 times 10 to the 9th.
Do you have to memorize what K equals?
No, I'll give them all. I'll give all this stuff. Okay? So, let's do this. Yeah. Okay. From this, like, I'm just going to pretend like this 4 coulomb charge is all by itself. Okay, let's go a distance 4 meters from that charge. What is the electric field right there? Don't panic. Just go back and say, where did I give you an equation for E? And then look it up and fill in the information. Sorry? Yeah, you're trying to find the electric field. So there is no charge here. This is just a point in space that is a certain R from this. Oh no. Alas, I have no libations to slake my thirst.
Drink some salsa. It's good. It's especially watery today, so it's like a beverage.
And oniony, tasty, sour.
Yeah, it's so good. But if I have a burrito, is there like a thingy where I put in a lot of salsa to make like the mixture?
I don't know. You can ask the seller.
And that's
Okay. Let's see. What did we get? Sarah, what'd you get? What's that?
A really large number.
That's fine. So how did you do it, first of all?
I did 9 times 10 to the 9 times 4 over 4 squared.
So she just used this, right? Now this is convenient because that's a 4 and that's a 4, so that's going to go away. So you get 9 divided by 4, which would be 2.25 times 10 to the 9th.
Is what?
Why is
Is that 2.15? What is that?
2.25. I know. I just did that mental math. I don't know if it's right.
What's the cube? Just that one?
Because I asked you only for this here.
Oh, so just
I'm not going to ask you for 2. I'll ask you for 1.
what?
Then you have to use vector math.
No.
Yeah. Because then what happens is there's one, it's like one vector's like this, the other vector's like that. You have to crack them into their pieces and add them together. Which part? Yeah. So I just took 9 times 10 to the 9th times 4 divided by 4 squared. That 4 knocks out that. 9 divided by 4 is 2.25, so it's just 2.25 times 10 to the 9th. I don't even need a calculator. What, you're gonna go do something?
Yeah.
Oh.
Want me to do that?
Yeah. I was waiting for you to go. At any point. Oh. Are you too old?
I'm going to talk about the basketball.
Oh.
That's so cute.
somewhere else and ask. But that's fine.
Is that recorded too?
That's recorded.
Right on!
Except it's not very, it's just silence.
Aw.
Because it was all quiet. Okay, wait.
How sensitive is your microphone?
But no. Go online, find out. Yeah, so that's this. So those are 2 problems that you could have had. The other problem that I could give you is, finally, give me the electric potential at that point. Because remember, electric potential, the equation comes out to be this. It should be quick. Come on, look at it, see it. It's just 9 times 10 to the 9, because the 4 cancels with the 4, right? Okay, but that's an example of what kind of questions I could ask you on that part of it. Okay? So, well, I mean, I combined it there.
Oh, because you isolated that last part. What did you combine?
Sure. I could say all of that. I could just give you one charge and say all that stuff. And say, go for it.
Will we have to add all of the different distances?
No, well, and there's some fun ones, right? For example, like I could do this.
You say fun.
Yes.
What?
What does that even mean?
Okay. So this is some sort of ball on the end of a string, and then I could ask you which direction, if this is a positive Q, if it's a positive charge, what direction, like how do you orient the electric field, and how strong is the electric field to make it hang at this angle? Well, you see a ball on a string, what's the first thing you should do? Yeah, force diagram. Boom, boom, boom. How did I know there's a force like that? Yeah, because it's hanging that way, right? Then I break this, let's call this T, this is Ty, that's Tx, do some of the forces, and I'll get my answer. Thank you, and see you tomorrow. Tomorrow we will do 2021, meaning circuits.